Today we're going to look at unions, intersections, and probability. Our objectives are to be able to find the probabilities from a Venn diagram, to be able to find probabilities of unions, and to be able to find the complement of an event. So what probabilities are represented by a Venn diagram? You can find lots of different things within it, and what we're going to be mainly talking about are intersections and unions. So if I have two events, event A represented by this circle, and event B represented by this second circle, and we're going to call this entire box the sample space, any possible event that can occur. So if I look at where the two circles overlap, that's called an intersection. That's where events A and B happen at the same time. So for example, if A is the event that you're a girl, and B is the event that you're in a sport, this overlap would be the girls that are in sports. And we use an upside down U for our intersection symbol. But we also have unions, and unions is the combining of all of the events. So basically where events A, B, or A and B both occur. So if I want A union B, I want all the girls, all the people who play sports, and any girl who plays sports. So I want just girls, just people who play sports, and the girls that play sports. That would be the union. The space on the outside is where you're not a girl and you don't play sports. Okay? And we're going to go through and look at some problems. And the second part is, what is the complement of events? So if I talk about event A being the circle, A prime is the complement of that event. So A prime is the complement of event A, and A prime are the events that are not in A. So for example, if A is the fact that you're a girl, not A, okay, or A prime is all of the events where you're not a girl, so when you're a boy. Okay? If I take the probability of event A happening plus the probability that not A happens, it should always equal 1. Our sample space, this big box, should always total up to 1, and that's going to be very important for the examples that we go through next. So you're going to see something like this on a quiz. I'm going to give you a sample space, and I'm going to just keep it simple with events A and events B, and I'm going to give you the individual sections. So this little crescent right here, this little moon-looking part, are all the events that are just event A, so that's 0.32. This middle section is the probability that you overlap A and B, which is 0.09, and then this little crescent on the right-hand side are just the events that are only in B, 0.27. But if you remember, this entire sample space has to equal 1. So if this entire thing has to add up to 1, I know I'm missing something, because if I add up 0.32 plus 0.09 plus 0.27. So if I add all this up, I get 0.68. So there's still 0.32 remaining, and that's what's going to be on the outside. So there's a 32% chance, or a 0.32 probability, that you don't fall into either of these circles. We're going to put that on the outside. So now what I'm going to ask you is a series of questions. What's the probability that you fall in event A? So if I look at event A, that's this circle. So those are the events that are 0.32 plus 0.09. So everything that's in this circle, which are these two parts right here. If I add that up, I get 0.41. Okay? So I could also look at the events that are not in B. So let's kind of think about that. What events are not in B? So if I kind of go through there, let's kind of erase this. So if I look at the events that are not in B, if I circle those, it would be this event and this event. Those are the ones that are not in circle B. So if I add those up, I get 0.64. So event B, not in B, is 0.64. Okay, well, let's go on. What about A union? Okay, union looks like a U, B. So our word for union is or. So A or B. So that means you're either in circle A or you're in circle B. So if you think about that, if you're in A or you're in B, it would be these three. Because this one isn't in A and it's not in B, so I just want these three. So if I add up these three, which I've already done, okay, that's 0.68. Okay, so what about this example? You're not in A, intersect, which we use the word and, you're not in B. So where would the values be that are not in circle A and they cannot be in circle B? So the values that are not in circle A, so here's circle A, would be these two. But I know it also cannot be in circle B. Well, this value is in circle B, so the only option I have is 0.32. Again, that's the probability that you're not in circle A and not in circle B. Okay, what if I want you to be in circle A and not be in circle B? So let's think about that. You have to be in circle A, so that would be just these two values, and you cannot be in circle B. Well, if I look at these two values, this 0.09 happens to be in circle B. So the only values that are in circle A but also not in circle B is this value right here, 0.32. And our last one, not A union B, or not A or B. Okay, so anytime you have this or, this union, you're going to be adding things together usually, okay? And anytime you have an intersection, you're going to be looking for the overlap. So intersection is our overlap, union is kind of our common combining of values. So you're not in A, so if I think what values are not in A, that would be these two. Or you could be just in circle B. So I can either I can have these in addition, because our ors are addition. I want anything that's in B. Well, this is already in B, so I've already counted that, and then I'm going to include this. So again, anything that's not in A or in B, I'm going to count. So this is not in A, or it could be in B. So if I add up these three together, 0.09 plus 0.27 plus 0.32, I'm going to get 0.68. Okay, we're going to go through another example. I'm going to show you a different strategy of how to come up with these. This one I just kind of talked through because I understand unions and intersections, but what if you get stuck a little bit? So, again, it's very similar. I know I need to have a whole sample space that adds up to 1. So if I add this right now, 0.43, 0.10, 0.25, I get 0.78. Well, that doesn't add up to 1, so I know I'm missing something. And if you could tell, I don't know how much is in this little crescent here for B. The events are just in B, but not in A. So I'm missing 0.22. That's what I'm missing to add up to 1. So here's a way to do this, and this might be a little bit more helpful. What is not in A? So if I think these are in A, these are the two that are not in circle A. So again, like if here's circle A, so I cancel all that out. I only care about the stuff that's not in A, so there'd be those two. So if I add that together, I'm going to get 0.47. So that's all I'm going to care about, is 0.47. The second one says, well, I want everything that's in B, so I care about everything that's inside this circle. Well, if I think about what's inside that circle, it's 0.10 and 0.22, so that's going to give me a value of 0.32. So those ones are pretty straightforward because it's either in the circle or not in the circle. But when it gets more complicated, our ors are our ands. So let's kind of look at our ors. Those are our unions. So I'm going to deal with these two first, and I'll show you the other ones. So what I like to do is I kind of like to think about circles and squares. And I have two different colors, so I could just do two colors of circles. But since you typically on a quiz or test won't have two different colors, I'll do two different shapes. So I have circles and squares. So what I want to do is I want to put a circle around anything that's not in A. So this is not in circle A, and this is not in circle A. I want to put a square around anything that's not in circle B. This is not in circle B, and this is not in circle B. So if you do this, it can be really easy if you kind of go through. I want anything that's not in A or not in B, or anything that has a circle or a square around it. So what has a circle or a square? Well, this is a square, this has a circle, this has a circle and a square. So anything that is circled or marked is what I'm going to add up. Well, if I add those three things together, I get 0.90, or I could just think, well, I know the whole thing adds up to 1. If I subtract 0.10, I get 0.90. So my answer is 0.90. Okay, so let's try this one. Anything that's in A, again, I'm going to do a red circle for A, my blue little square for not B. So I want anything that's in A, which would put a red circle around, or anything that's not in B. Well, this is not in circle B, and this is not in circle B. So I'm going to add together anything that has a circle or a square around it. So basically anything I marked up. Well, since I marked these three, okay, if I add 0.43, 0.10, and 0.25, I already have that here, I'm going to get 0.78. So my answer is 0.78. That's how you can do the OR ones, pretty straightforward. So what about the AND problems? Okay, so remember intersection means AND. I'm going to start off the exact same way. I'm going to talk about red circles for my A's and little blue squares for the B's, or whatever it asks for. So let's go through this one. Let's do this one first. I'm going to put a circle around anything that's an A, and I'm going to put a little square around anything that's in circle B. But now it's not an OR. It can't have a circle or a square. It has to have a circle and a square to be counted. Okay, so I want the intersection of these two things. So the intersection of where the red circles are and the blue squares. So if I look, the only place where I have a circle and a square is right here at 0.10, and that will be my answer. So 0.10 is my answer. So let's look at the last one. Not an A, so this is not in circle A, this is not in circle A, and B, this is in circle B, this is in circle B. So again, I want anything that has a circle and a square. The only part that has a circle and a square is 0.22. So my answer is 0.22. And that's how you deal with the Venn diagrams on a simple, kind of straightforward basis with two events A and B. But what we're going to be dealing with is more complicated problems dealing with unions. Okay, but our unions actually deal with intersections as well. So we want to find the union of two events. And how we actually say this is the probability of A or B, or A union B, should equal the probability that event A happens plus the probability that event B happens minus the probability that A and B happen at the same time. Okay, so basically if I want A or B, okay, so if you remember from our little circles, A or B is when I add all three of these parts. It could be an A by itself, it could be in B by itself, or it could be in the intersection of A and B. Okay, so it's combining all three of those together. Well, probability of A would be this entire circle. Probability of B would be in this entire circle. But if you notice, I've counted this middle part twice. The time when I shaded it blue and the time when I shaded it red. So what we're going to do is we're going to subtract that middle part one time, and that'll give me just the red part, just the A part with blue, just the red part in B, and then one time of the overlap. And that's what our formula gives us. So we're going to go through 5 examples of how to use this formula. So it says, please select one card. And you have to know that when we're talking about unions, we're doing one thing at a time. Okay? So please select, or usually for our least basic problems. So please select one card from a standard deck of cards. Okay, remember that has 52. Find the probability of being a club or a face card. So I'm pulling a single card out of the deck. I want to know what's the chances that it either falls in the club category or the face card category. And technically, because it's a union, it could fall in both categories and still count. So if I write out my formula, this is going to be the probability that it's a club or a face card. I'm just going to use FC for face card. So that means I want to find the probability that it could be in the club category. I'm going to add that to the chance that it's in the face card category. But I need to subtract any card that falls into both categories. So the reason I have to, again, subtract that is if I count all the clubs, okay, and if you remember there are 13 clubs, ace through king. So the probability it's a club is 13 out of 52, again, because I'm selecting one card. The probability that's a face card, well, if you remember there are 12 face cards. Jack, Queen, and King of the hearts, clubs, spades, and diamonds. But if you notice in this category, I counted the Jack, the Queen, and the King of clubs. Okay? But in this category, I also counted the Jack, Queen, and King of clubs. So I counted those 3 cards twice. That's why we have to subtract any card that's a club and a face card. Well, that would be the Jack, Queen, and King of clubs, which is 3 out of 52. And I only subtract it once, because if I subtract it once, I take it away from one of these categories. So if I add all this together, 13 over 52 plus 12 over 52, again, we add and subtract, we go left to right, that's 25 over 52, minus 3 is 22 over 52. And you could just leave it as the fraction if you would like. I don't mind if you don't reduce it. If you're going to, I prefer either giving me personally a decimal or leaving it like this, because I think this gives me more information about what the problem is than giving me a reduced fraction. So let's look at number 2. There are 92 students total. We always like to know what the totals are. 44 students are enrolled in science, 65 are enrolled in math. 39 students are enrolled in both math and science. If one student is randomly chosen, again we're talking about doing one thing, what is the probability that the student is enrolled in math or science? So again, I want to know what's the probability that they're in math or science. To find our union, we're going to take the probability of the first one, math, plus the probability that they're in the second one, science, and we're going to subtract the probability that they're in both, math and science. Okay? And it seems like a long formula, but after you do a couple of examples, it's pretty quick to write it out. So I know my totals, and whenever you're doing these union problems, your denominator should be the same every time. So sometimes I like to just write that in first. It said 44 students are enrolled in science. And be careful of how the problem is worded as opposed to your formula, because it might not always go from left to right. So 44 students are enrolled in science, 65 are enrolled in math, and 39 are enrolled in both math and science. Okay, so again, I'm just going to add left to right. This is over 92. 65 and 44 is 109. So if I subtract 39, I should get 70. So again, you give me a decimal if you like, but I'm okay with just 70 over 92. And that's the chance, if there's 92 kids, 70 of them would raise their hand if I ask if you're in math or a science class. The third one says, Luke's closet contains several types of shirts, 3 white, 8 red, 10 green, 7 black, and some blue. Luke picks one shirt out, again we're talking about one thing, out at random without looking at the type. The probability that the shirt you picked is red or blue is 7 over 17. How many blue shirts are in Luke's closet? So again, I know anytime you see this red or blue, I'm going to use my union formula. The probability that it's red or blue equals the probability that it's a red shirt plus the probability that it's a blue shirt minus the chance that there's a shirt in there that's red and blue, because it would have been counted in both categories. So I already know the probability that it's red or blue is 7 over 17. So they actually gave me the left side answer. And I know this is what my formula looks like. So I really need to know the total. So if I go back to thinking about what's in Luke's closet, 3 white, 8 red, 10 green, 7 black, and some blue. This is the problem. I don't know how many blue there are, which means I don't know the total number of shirts. If I did, it would be really easy. I could just subtract those. So I'm going to have this variable in the problem. So if I add this together, I have 10, 25, 28 plus so many blue. So that's my denominator, my total of number of shirts inside Luke's closet, where X represents the number of blue shirts. But how many red shirts are in there? Well, if I look, there are 8 red, so I can put 8 here. How many blue? Some blue, so I'm going to put an X. And they didn't tell me there were any that were a combination of colors. So I have 0 shirts that are red and blue. So now that I have this, I can simplify both sides. I have my common denominator of 28 plus X. 8 plus X minus 0 is 8 plus X. And now what I'm going to want to do is cross multiply. So 17 times 8 plus X equals 728 plus X. Okay, now I'm going to distribute. So if I do this, 56 is 136. 6 carried 5, yep. Plus 17x equals, again, if I distribute on this side, 6, 5, 196 plus 7x. Let's continue my work up here. I'm going to try to get the x's on one side, the numbers on the other. So what I'm going to end up getting is if I subtract 7x, I'm going to get 136 plus 10x equals 196. Subtract 136, I'm going to get 60. Divide by 10, I'm going to get 6. And since x represented a number of shirts, there are 6 blue shirts in Luke's closet. And you could always substitute it back into your formula, kind of make sure everything works out. But again, we shouldn't get a decimal answer because that wouldn't make sense. So if you get a decimal, you know you made an algebraic mistake somewhere. So we're going to look at our last two examples. And number 4 says, what is the probability of choosing one card, again we're doing one card, from a standard deck of 52 cards and having it be an 8 or not a spade? This not a spade means that it's the complement of being a spade. So it's all the cards in the deck that are not spades. But I see this or, so it's my union, so I'm going to write out my formula. What's the probability that's an 8 or, and I'm just going to do this, not a spade. I'm going to do my little prime, not a spade. You could write not spade if you want to do that. This equals the probability that it's an 8 plus the probability that it's not a spade, okay, minus the probability that there's a card in the deck that's an 8 and it's not a spade. Okay. So I'm going to go through this, and if you remember, the denominator should always be the same because we're dealing with the same total, because we're just doing pulling one card from the deck. I want to know how many 8s are in the deck. Well, that's one of our values. There are 4 of each value. I want to know how many are not a spade. Well, a spade is one of our suits, and there are 13 of each suit. So if there are 13 spades out of 52, if I subtract 13 from 52, I get 39. So there are 39 cards in the deck that are not spades. Those would be the clubs, hearts, and diamonds, or 13 times 3, or 39. Minus, how many cards are in the deck that are 8s, but they're not a spade? Well, there are 4 8s in the deck. One of them happens to be a spade. So there are 3 cards, the 8 of hearts, 8 of diamonds, and 8 of spades. I'm sorry, 8 of clubs that are not spades. So I'm just going to combine like terms. Common denominator of 52. 4 plus 39 gives me 43. Minus 3 is 40. So what this means, then, in a standard deck, there are a total of 40 cards. So if you took a deck of cards in your hand, and any time you had an 8 or a card that was not a spade and set it off to the side, if you counted that pile down, there'd be 40 cards in there. There'd only be 12 cards that don't fall in this category. So it means there's only 12 cards that are not an 8 or a spade, if you kind of do the complement of each of these. Okay? That would be the ace, 2, 3, 4, 5, 6, 7, 9, 10, jack, queen, and king of spades. Those are the only 12 cards that would be left on the side. In our last example, there are 15 blue marbles, 12 red marbles, 13 yellow marbles, and 16 orange marbles in a bag. Find the probability of picking at least one red marble if you choose 6 at random. In the past, we've been dealing with at most one problems. This is at least one problem. Anytime you see at least one problem, we want to deal with the problem as a complement. And I'm going to show you why. If I'm choosing 6 marbles out of this bag, so 1, 2, 3, 4, 5, 6, I actually have 7 different ways that can happen. So let me show you this quickly to hopefully give you a little visual of what's actually going on in this problem. So I'm picking 6 marbles. And there's lots of different ways that can happen. But if I'm concentrating on the number of red, if I want at least one red, my one option could be no red. Okay, or there could have been 1 red. Or there could have been 2 red. Or 3 red. Or 4 red. Or 5 of them are red. Or all 6 of them could have been red. Now the reason why these are all possible options is because there are a total of 12 red marbles in the bag. So if I'm picking 6, there is a possibility that 3 of them, 4 of them, 5 of them, up to 6 of them are red marbles. So there are 7 different options if I pull out 6 marbles from a bag, and I'm just choosing them, that I get all of them. These are all the possible options for reds. But I want at least 1 red. So at least 1 red means I have 1 red, 2, 3, 4, 5, or 6 red marbles. Okay. The only one that it does not count is getting no reds, because if I need at least 1 red, no red doesn't count. So I could find the probability that I get 1 red, or 2 reds, or 3 reds, or 4, or 5, or 6 reds. So this would be 1 red, or 2 red, 3 red, or 4 red, or 5 of them are red, or 6 of them are red. And we talked about this before, that when I have these ors, I would have to add all of these different probabilities together. I'd have to find what's the probability that I choose 6 and one of them is red, or 2 of them is red. And I would have to find this probability and add it to this one and this one and this one. So this is 6 problems that I would have to do separately. Okay, so this is what I want. So if this is my sample space, okay, and event A is the fact that it's at least one red, that's what I would have to find. It's a lot of work. But what I could do instead is just find anything that's not in event A. So if event A is at least one red happening, not A is the fact that no reds happen. And that's much easier to find because it's one problem. Well, since I know the probability of A plus the probability of not A should equal 1, if I want to know what the probability of A is, I could just do 1 minus the probability of not A happening, okay, by subtracting this over. So that's what I'm going to do for this problem. Anytime you have an at least one problem, you're going to have a lot of sub-problems to do. And because it says at least one, the only thing that's not in this category is 0. So that's what I'm going to find. I'm going to do 1 minus the probability of pulling no reds. This is a much easier problem. So how do we do that? 1 minus, okay, I am choosing 6. So if we think about this problem, if I add all this together, 15, 12, 13, and 16, so let's see. This is 25, 30, 40, 56 total. Okay. And if you remember from some problems we did before, and I'm just going to erase some of this stuff just to give us a little bit of room now that I've kind of talked about it. So, okay, so I have 56 total marbles. Of those, I know that 12 are red, which means that 44 are not red. If you remember, we did this before. If I'm choosing 6 total, and I want 0 of them to be red, that means that all 6 of them are not red. So again, I want to find the probability of at least one red. And to do that, I'm going to do 1 minus the probability of its complement, which is none of them are red. So I'm going to do 1 minus the probability that none of them are red are 12, choose 0, which anytime you're choosing 0, you don't have to write it. So I'm just going to do 44, choose 6, minus, I'm sorry, over 56, choose 6. So this is a probability that I choose 6 and none of them are red. But remember, that's not what I want. I actually want the complement of it, so I'm going to do 1 minus. So, again, you can just take your calculator. Okay, let's pull that up. Clear it out. I'm just going to do 1 minus, and I'm just going to use parentheses. I'm going to do 44, choose 6. Okay, and I'm going to divide that by 56, choose 6. And that's going to give me my decimal. So I'm going to get approximately 7826. So the probability that if there are these 56 marbles in a bag, that I pick 6 and at least one of them is red, I have a 78% chance that, or over 78% chance that at least one of them will be red. Because the only chance that I don't have of this happening is when none of them are red. And you could see if this changes to a fraction. You know, you don't have to. That's kind of a nasty fraction. So these kind of problems, it's probably better just to leave it here as your decimal. I hope you feel a little bit better about being able to find probabilities from a Venn diagram, to be able to find probabilities of unions, and to be able to find the complement of an event.